Hello, friend, and welcome to Fall Asleep to Astronomy. I'm so glad you could join me in this quiet, shared moment. The world outside can feel distant and hushed, and we have the chance to turn our attention to the soft silver glow of the cosmos. Let the night gather around you like a warm blanket. We're going to share a fascinating little secret of the deep sky, a mysterious, icy traveler that has already swept past our sun and is now slipping back outward. 3I Atlas. Imagine this ancient, cosmic snowball, flaring softly as it rounded the sun and now drifting away again into cooler, darker space. We'll gently uncover the story of this wanderer, trace its unexpected glow, and listen for the quiet truth of what is actually happening with this particular celestial visitor. If these peaceful nighttime explorations bring you calm or spark a gentle wonder, please consider offering a quiet like and a soft subscribe. It helps guide other sleepy souls to this space too. For now, there's no hurry, just the warmth of this moment and the long, silent path of a comet still gliding through our solar system, waiting for us to follow. Close your eyes, and let's begin our gentle drift together. There is, right now, a strange little traveler sweeping through our solar system, moving in a way that hints it does not quite belong here. We do not fully know what this object is or what story it is carrying. It has already slipped out of easy sight, lost in glare and distance, so we cannot simply point a telescope and watch it glow whenever we like. And yet, for months, people on this planet have been following its path with patient attention, turning raw numbers and faint traces of light into a picture of a guest just passing through our neighborhood. This visitor has been given a careful, technical label, 3I Atlas, and a gentler description as well, an interstellar comet, a small, icy body that seems to be arriving from the deep space between the stars. In only a few months, scientists have written nearly 100 research papers about 3I Atlas, each one a different attempt to listen closely and make sense of what the data is whispering. Around those official records, there are also other ideas and speculations. It can feel like a lot of noise around a very quiet object. So instead of chasing every rumor, imagine us sitting together and gently sorting through what is steady and what is certain. If we keep only what is grounded in observation, what remains is still deeply interesting. At the center of that careful work is a simple question. Where is 3I Atlas now? And what is it actually doing as it completes its swing around our sun and begins to head back out? Not long ago, 3I Atlas passed through the closest point of its swing around our star. Astronomers use an old word for this part of a path, perihelion. It means the moment when a journey brings something as near to the sun as it will ever come before it begins to drift away again. For 3I Atlas, the peak of this close approach came on October 29th, when it slid to within about 210 million kilometers of the Sunday 6. That number is so large that it can be hard to hold in the mind, just a string of digits without shape or feeling. To make the vastness a little more familiar, people who study the sky use a standard stride called an astronomical unit. One astronomical unit is simply the average distance between the Earth and the Sunday. Using that as our measuring stick, the perihelion of 3I Atlas happened at about 1.4 astronomical units from the Sunday. That tells us that this comet never swoops dramatically close to the solar furnace. It does not dive down toward Mercury or skim just above the boiling surface. Instead, it passes somewhere just inside the orbit of Mars, near enough to feel the heat stronger than usual, but still within the cool outskirts of the sun's reach. Even so, for a fragile, icy body that has spent most of its existence in deep cold, this is as hot as things are ever likely to get. Perihelion is the time of peak activity for 3I Atlas, the moment when its surface begins to change most strongly. Sunlight that has traveled from the face of our star lands on this small object and starts to work on the material it is made of. Bits of frozen gas and dusty ice near the surface can no longer stay still. They begin to break free and flow outward, leaving the solid heart of the comet and spilling into the surrounding space. This shedding of material sounds dramatic, but it is familiar behavior for a comet. There is a clear word for it: sublimation. Sublimation is what happens when a solid turns directly into a gas without pausing in a liquid state in between. On the surface of the Earth, we sometimes see something similar when ice slowly fades away into the air on a dry, cold day. Out in the vacuum of space, there is no room for puddles to form and linger. When ices warm up out there, they tend to skip the liquid stage entirely, changing straight from solid crystals into wandering molecules that lift off and leave. As that happens on 3I Atlas, the comet begins to grow the look that makes such objects feel both eerie and beautiful. Around the firm center, or nucleus, of the comet, a hazy envelope starts to shine. This is made of the gas and grains of dust that have been freed from the surface and are now floating in the space immediately around it, forming something like a glowing hood or veil. Astronomers have a precise name for this soft blur surrounding the core. They call it the coma. From far away, in a telescope image, the coma can look like a little smudge of light, slightly brighter at the center, fading at the edges. Then there is the tail, the part of a comet that most people picture first, the long, streaming band of pale light that stretches away into the dark. The tail exists because the sun is not only a source of light and warmth, but also a steady fountain of charged particles and energy. This outflow is called the solar wind. Waves of radiation and particles flow outward from the sun in all directions, rushing past planets, dust, and lonely stones. When this invisible wind meets the material in the coma, it pushes on the lightest bits of gas and dust, sweeping them away from the comet and stretching them out like a banner that always points roughly opposite the sunday. The result, when we are lucky enough to see it, is a small, shining body with a soft head and a trailing tail, moving steadily against the background of stars. It is a slow and graceful piece of cosmic choreography, a dance between ice, sunlight, and wind as the comet approaches and then recedes from the sunday. For 3I Atlas, that dance reached its liveliest steps at perihelion, when its surface was warmest, and it is still unfolding now as the comet glides back toward the outer dark. From our point of view, though, much of this performance is taking place behind a curtain. Around the time 3I Atlas was passing through this most active part of its journey, and for a little while afterward, our line of sight from Earth ran almost directly into the sun's brilliance. The same light that makes the comet wake up and shine also drowns out our ability to watch. It is a little like knowing that there are fireworks bursting open just beyond the edge of a building. You can see the sky brighten, and you can feel that something is happening, but the details are hidden. For the moment, the glare of the sun still blocks our clearest view, and we have to wait for the geometry to shift. So we find ourselves in a waiting period. We know where 3I Atlas is in its path, and we can describe what the sunlight is doing to its surface and its halo of dust and gas. Yet we have to be patient for the comet to move into a darker patch of sky away from the blinding line between our world and our star. before we can study it in more comfortable detail again. While we wait, there is room to look backward instead of outward, to trace how this traveler first came into our awareness. That story begins not in space itself, but in small domes and metal structures scattered around our planet, places where telescopes keep watch over the night. Since July of the year 2025, this comet has been followed by a network known as the Asteroid Terrestrial Impact Last Alert System, or ATLAS for short. Rather than being a single instrument, ATLAS is more like a team of eyes. Telescopes in locations such as Hawaii, Chile, and South Africa take turns staring at wide patches of sky, night after night, looking for anything that moves against the fixed backdrop of distant stars. Most of the time, what those telescopes find are ordinary wanderers, small asteroids in familiar paths, bits of rock and ice that loop the sun on predictable schedules. From the point of view of the cameras, these objects show up as tiny points of light that shift just a little from one image to the next. On the night of July 1st, one more of those small moving specks appeared in the data. At first glance, it was nothing unusual. The people watching classified it as a new asteroid, added it to the list of objects to keep an eye on, and prepared to turn their attention to the next faint trace. But as more images came in and more careful measurements were made, something about this particular point of light began to stand out. When they traced its position across multiple nights and did the math that turns changes in angle into real motion, they realized that this object was crossing space faster than expected. It was as though a car had appeared on a road where everyone usually drives at a steady speed, and this one vehicle was gliding along well above the usual pace. Nothing about its brightness looked especially alarming. It was the path and the speed that refused to fit into the familiar patterns. To understand why that matters, it helps to hold a simple picture of how things move in our solar system. Everything here, from planets to pebbles, is in motion all the time. The sun's gravity acts like a deep, wide well in the fabric of space, pulling on every object and trying to draw it inward. If something were perfectly still above that well, it would simply fall straight down toward the Sunday. But almost nothing is perfectly still. Planets, comets, and asteroids are all moving sideways as they feel the pull downward, and that sideways motion bends their paths into loops. You can imagine it the way you might picture a marble rolling around inside a smooth bowl. If you drop the marble straight down, it will fall to the center and stay there. If you give it a gentle push so that it has some sideways motion, it will circle around inside the bowl, looping and looping without falling in. In the same way, the Earth and the other planets keep circling the sun, always being pulled inward by gravity, always moving quickly enough sideways that they do not tumble straight into the central fire. There is a quiet rule in this dance. The closer you are to the sun, the faster you have to move to keep from spiraling inward. Objects on the inner tracks, like Mercury and Venus, race along their orbits. Those farther out, like Jupiter or Saturn, travel more slowly. The speed of each world is tuned to its distance, balanced between falling in and flying away. For most of the rocks and ice in our solar system, that balance holds them in long-term orbits. But if an object moves fast enough, that balance begins to shift. Imagine giving the marble in the bowl a much stronger push. Instead of settling into a gentle loop around the center, it climbs higher up the sides of the bowl with each pass. Its path grows longer and wider. Keep increasing the speed, and at some point, the marble will have enough energy to roll up and out of the bowl entirely, never to be pulled back in. In space, the same thing can happen. When something's motion becomes great enough, it is no longer caught in a closed loop around the Sunday. Its path stretches out and opens up, allowing it to rise up out of the gravitational well and head off toward the wider darkness beyond. Speed, in this picture, becomes more than just a number. It is the quiet key that decides whether an object will circle for ages in the sun's embrace, or whether it will climb up and away, out into the wider dark. If you keep adding a little more speed, the orbit stretches and lengthens. The circle becomes an oval. The oval grows thinner and more drawn out. And if you reach a special threshold, a certain velocity that tips the balance, then the path stops closing on itself at all. The object is no longer just looping around the Sunday, it is on its way out. Once that threshold is crossed, the sun's gravity still tugs, but it can no longer pull the traveler back into a bound orbit. The object is free to slip out of the family of planets and wander into the empty stretches between stars. That in-between place is not truly nothing, but it is close, a vast, thin ocean of dust and gas, so spread out that for long periods you could drift without meeting anything at all. To move from being a child of the solar system to a visitor of interstellar space, you need that extra push of speed. When astronomers first measured how fast this new object was moving, they had to look twice. They took the faint points of light from different nights, turned them into positions, turned the positions into a path, and then into a velocity. The answer that came back was not gentle, it was shocking. This little body, at the edge of our awareness, was racing faster than anything else we had ever tracked passing through the solar system. Among all the known planets, moons, comets, and asteroids, nothing we had seen before was moving quite like this. It helps to place that in a frame you can hold. Think of the Earth itself, the ground beneath your feet, circling the sun at about 30 kilometers per second. Every second of every day, our whole world glides through space by a distance you could barely imagine walking in a lifetime. That is already very fast, and Earth is not especially far from the Sunday. Yet there are worlds that huddle even closer to the heat, and therefore must hurry along more quickly to keep from spiraling inward. Mercury is one of those worlds, the innermost planet, orbiting at about 0.4 astronomical units from the Sunday. 1 astronomical unit is the average distance between Earth and the Sun, so Mercury's path lies well inside our own. Down there, in the region where sunlight is harsh and unfiltered, Mercury gets baked. To avoid plunging deeper into the gravity well, this small planet has to race around the sun at roughly 48 kilometers per second. It is like a tiny runner hugging the inside lane of a track, legs moving furiously just to stay where it is. Now picture our new visitor, the object eventually named 3I Atlas. When the Atlas telescopes first picked it out, it was still far from the Sun, just inside the orbit of Jupiter. That is around 4.5 astronomical units away, a region where the sunlight is softer, the temperature low, and most things move more slowly along their paths. Yet at that comfortable distance, 3I Atlas was already traveling at about 58 kilometers per second. You can let those numbers sit for a moment. Mercury, pressed close to the Sun, runs at about 48 kilometers per second. 3I Atlas, far out near Jupiter's realm, was already moving 10 kilometers per second faster than that. It was like noticing a small stone sailing through the outer lanes of a racetrack, where most runners jog, yet somehow it is sprinting faster than the champion sprinters on the inner circle. At such a speed, there was no question about what would happen next. This object was not going to be captured into a polite orbit around the Sunday. It was going to blow straight past the inner system, curve around our star once, and then keep right on going. The shape of its path sealed that conclusion. Instead of tracing a closed loop like a circle or an ellipse, the orbit of 3I Atlas is what astronomers call hyperbolic. A hyperbola is a kind of open curve. If you tried to follow it with your finger, you would never return to where you started. For this object, a hyperbolic trajectory means it did not begin life as part of the Sun's long-term family. It came in from interstellar space on an open track, is taking one sweeping turn near the Sun, and then will drift back out into interstellar space again, never to rejoin us. That realization changed how people spoke about it. It was no longer just a new asteroid in a catalog. It became the third known member of a very small and special group. Interstellar objects passing through our solar system. That is where its official name comes from. 3I Atlas. The 3 marking it as the third interstellar visitor discovered, the I for interstellar, and Atlas honoring the survey that first found it. Third, which means there were 2 others before it. The first was a visitor you may have heard of, Oumuamua. Discovered in 2017, it was the first confirmed object from another star system ever seen passing through our own. Oumuamua behaved in ways that puzzled astronomers deeply. Its shape, its brightness, and the way it moved under the Sun's influence were all different enough from normal comets and asteroids that it still inspires debate and curiosity. We will leave the details for another time, but it is fair to say that Oumuamua was wonderfully strange. The second visitor, named Borisov, was different in a calmer way. Officially called 2I Borisov, it arrived not long after Oumuamua and did something almost comforting. Aside from being on a hyperbolic path that marked it as interstellar, it acted very much like an ordinary comet. It grew a coma and a tail in a familiar way. Its behavior matched what we expect when a small icy body from the outer regions of space warms as it approaches a star. In that sense, Borisov was weirdly not weird. It showed that not every interstellar visitor has to be deeply exotic. Some can be surprisingly normal in their habits. 3I Atlas joins this tiny family, but stands apart from its siblings in some important ways. There are 3 big differences that make this new object particularly intriguing: how big it is, how fast it travels, and the direction from which it has arrived. In terms of size, 3I Atlas is literally larger than the 2 that came before. Oumuamua, as best we can tell, was no more than a few hundred meters across, perhaps up to 400 meters along its longest dimension. It was like a mountain ridge fragment or a skyscraper-sized shard drifting alone in space. Borisov, the second visitor, was broader, roughly 1 kilometer wide, more like a modest town squeezed into a ball of ice and dust. By contrast, estimates for 3I Atlas suggest it could be up to 5.6 kilometers in width. That is several times larger than Borisov and many times larger than Oumuamua, more like a small city's footprint carved into a chunk of ancient material. Then there is the speed. We have already felt a hint of how quickly 3I Atlas moves compared to Mercury or to the worlds near the Sunday. When you compare it to Oumuamua and Borisov, the difference remains striking. Atlas is traveling at about twice the velocity of those earlier interstellar visitors. Where they were fast enough to escape the Sun's pull and follow open paths, this new object is even more energetic, rushing through our region of space as though in a hurry to keep an appointment elsewhere. For observers trying to collect data, that speed is both exciting and frustrating. It means less time to watch, fewer nights to gather light before the traveler shrinks back into the background. The third difference is the one that feels the strangest of all: the direction. It is one thing for an object to be fast or large. Many things in the universe are big and quick, but the angle at which 3I Atlas enters our solar system, compared to the way everything else is arranged, is what makes astronomers lean forward in their chairs. To feel why, it helps to remember that our solar system is not just a random cloud of objects scattered in every direction. Over billions of years, the gas and dust that formed our sun and planets settled into a shape that is mostly flat, like a disk. The planets, most of the asteroids, and many of the smaller bodies all move within this disk, tracing out orbits that lie close to a common plane. This thin, shared surface on which the planets dance is called the plane of the ecliptic. If you could step far away and look back, you would see the solar system as something like a shining coin, with nearly all of its mass and motion contained in that narrow thickness. There are exceptions, of course. Not every orbit lies perfectly on that plane. Pluto is the most famous example. Its path is tilted by about 17 degrees relative to the plane of the ecliptic. You can think of it as a small world that sometimes wanders a little above the main disk and sometimes a little below it, weaving its own gentle pattern through the three-dimensional space around the Sunday. Other minor bodies also have orbits that are inclined by various angles, giving the solar system a bit of thickness and texture. Because space is three-dimensional, a visitor from outside could, in principle, approach from any direction at all. It might plunge in from far above the disk, or sweep in from far below, or arrive from a direction tilted at some random angle. That is more or less what happened with Oumuamua. It came from the northern sky, from a general direction that lines up with the way our solar system as a whole is moving through the galaxy. You can imagine the sun and all of its planets as a group traveling around the center of the Milky Way, carrying their own local swarm of matter with them. Oumuamua appeared almost head-on along that path, so in a sense, we and that object met each other in the middle. We hit it, and it hit us at the same time. Borisov did something similar. Its path was not quite as straight on as Oumuamua's, more like a diagonal glancing approach, but it still came from largely the same general side, the forward direction of our motion through the galaxy. Both visitors arrived from above or ahead of the disk, like small stones thrown toward a spinning plate from the front. 3I Atlas is different. This is not another head-on meeting. Its path through our solar system is more like a side impact, the way one car might cross in front of another at an intersection. If you imagine the orbits of the planets as lines drawn on a flat sheet of glass, 3I Atlas is sliding in along an almost perfectly matching sheet, shifted only a little. Its track lines up with the disk of our solar system in a way that feels almost too exact. When astronomers say that 3I Atlas is only about 3 degrees off from the plane of the ecliptic, that number might sound small and abstract, but you can translate it into a feeling. Pluto's 17-degree tilt is enough to make its orbit clearly stand apart from the main planetary disk. 3 degrees is barely a nod. It is as if this interstellar visitor has chosen to skate almost exactly along the same level where our planets move, dipping only a tiny bit above or below. Because the universe allows so many directions, because a body arriving from interstellar space could, in principle, choose any angle in 3 dimensions, This near-perfect alignment feels like a kind of cosmic coincidence. Out of all the possible paths that could have brought 3I Atlas into our view, it has taken one that lines up almost exactly with the thin disk where our worlds reside. To have something from the deep between stars slide in so neatly along our shared plane, hitting us almost perfectly side-on, is a very big coincidence. When something from the deep between stars arrives on such a neatly lined-up path, it is hard not to feel a question forming. If 3I Atlas moves so fast, and if its track is so carefully aligned with our thin disk of planets, then where did this traveler begin its long journey? What kind of quiet corner of the galaxy shaped it and sent it drifting our way? We do know at least the broad direction it came from. If you imagine the Milky Way from above, like the familiar pictures in books, you see a broad spiral of light curling around a bright center. Our sun lives out in one of the spiral arms, not in the crowded core, but somewhere in the outer half of the galaxy. When you look up on a dark night and see the Milky Way as a pale band stretching across the sky, what you are really seeing is mostly the next spiral arm over from where we sit, a river of distant stars winding past our viewpoint. 3I Atlas, as best we can tell, approached us from the direction of the bright galactic center. That inner region looks so luminous because there are many more stars packed together there than in our quieter neighborhood. Their light overlaps and blends into a thick glow. It is easy to picture this as a busy downtown, full of motion and energy, while our sun drifts in something more like the soft outskirts of a vast city. But just as we reminded ourselves with the solar system, space is not flat. It is three-dimensional, full of above and below, as well as around. To really think about where 3I Atlas may have formed, it helps to tilt that top-down picture of the galaxy on its side, as though you picked up the Milky Way disk and turned it to look at its thin edge. Seen that way, some familiar patterns return. Just as most of the mass in our solar system lies in a thin disk around the sun, most of the stars and gas in the Milky Way lie in a relatively thin layer around its center. This is called the thin disk of the galaxy, and it is where you find many of the young, bright stars, dense clouds of gas, and all of the noisy events that mark active regions of space, collisions, bursts of star birth, and, eventually, supernova explosions. But, again, like our solar system, not everything belongs strictly to that thin sheet. There are stars and clusters that live a bit above and a bit below it, spread out in a thicker, more gently filled region. Astronomers call this the thick disk. It is still part of the galaxy, still circling its center, but it is less crowded. In the thick disk, there are fewer places where massive stars gather and explode, fewer packed clusters where gravity flings objects into chaotic paths, fewer black holes and violent events. Because it is quieter out there, things in the thick disk can lead long, undisturbed lives. They orbit and they age, and not much bumps into them. The current best guess is that 3I Atlas began its existence in this older, calmer part of the Milky Way, perhaps as a leftover fragment from the early days of star and planet formation in that region. If that is true, then this little comet-like object may be very ancient indeed. Some estimates place its age at around 7.66 billion years. That is a number you can let sink in slowly. The Earth itself is about 4.5 billion years old. So 3I Atlas could be nearly twice as old as our planet, a relic from a time when the galaxy was younger and the sun did not yet exist. While dust in our neighborhood was still gathering itself into the star that would one day warm your days and light your sky, this object may already have been circling quietly in a distant, dim orbit somewhere in the thick disk. We probably will never be able to draw its entire path from birth to now. There is too much time, too many small tugs and tiny nudges from passing stars and clouds along the way. But astronomers have recently managed to trace its motion back for a meaningful stretch, about 10 million years. By carefully rewinding the positions and movements of nearby stars and the object itself, they identified 93 stars that 3i Atlas would have passed by over that time. Here is where the story becomes strangely lonely. Over those 10 million years, the closest approach between 3i Atlas and any one of those 93 stars was about 0.3 light-years. In human words, that is roughly 63,000 astronomical units. An astronomical unit, remember, is the distance between the Earth and the Sunday. So for millions of years, this traveler wandered through space, without ever coming nearer than tens of thousands of times that distance to any star. During its recent close passage by our Sun, 3i Atlas came to about 1.4 astronomical units from our star. Compared to that long, empty trek, this was an intimate brush. For ages it has moved through the thin, cold medium between stars, scarcely touched by their gravity, and now, for a brief moment in its long life, it has glided through the inner region of a planetary system, close enough that we can notice its presence and measure its light. Even now, as it heads back outward, it is still moving through that inner realm, carrying the marks of its encounter. That closeness gives us a rare chance to learn, and we have already used it in a clever way. Even before 3i Atlas was officially announced as a new discovery on July 1st, 2025, it had already left a faint trace in the data of another observatory. The first time it truly appeared in our records was on May 7th of that year, in images captured by the Transiting Exoplanet Survey satellite, better known as TESS. TESS is a telescope that does not sit on the ground. It orbits the Earth, turning its gaze outward, watching large patches of the sky for tiny dips in starlight that can reveal planets passing in front of their suns. Its main job is to find those distant worlds, exoplanets circling other stars. But sometimes, while it stares in one direction for weeks at a time, other moving objects cross its field of view, leaving their own subtle marks on its cameras. For about a month, it so happened that TESS was looking in the same direction that 3i Atlas was traveling. Frame by frame, over days and weeks, the object crept across its images, shifting against the background of the fixed stars. That lucky overlap gave astronomers a chance to track 3i Atlas as it moved inward through the region of Jupiter's orbit, long before many other instruments were paying attention. One of the first things they wanted to understand was simple in principle. How bright was this object, and how did that brightness change over time? The way an object reflects light as it moves closer to the sun can tell us a lot about what it is made of and how its surface is behaving. During that 1-month stretch, when TESS could see it, 3i Atlas traveled roughly 1 astronomical unit closer to the Sunday. That is a big step inward, and with that step, more sunlight should fall on it. If nothing about the object changed except its distance from the sun, you would expect its apparent brightness to increase by a modest, predictable amount. Astronomers use the word flux for this kind of perceived brightness, the amount of light energy per second that reaches a given patch of detector, or, if you like, a small imaginary window in space. Flux is not about how bright something truly is at its source, but about how bright it seems from where you stand. You can picture flux with a simple thought. Think of the sun at noon on a clear day where you live. It is intense, but your body and eyes know how to handle it. Now imagine that same sun as seen from the surface of Mercury. The star itself has not changed. It is putting out the same amount of light. But because Mercury is much closer, each square centimeter of ground there receives more of that light. To a person standing on Mercury, if they could somehow stand there unharmed, the sun would look fiercely brighter, almost unbearable. The intrinsic brightness is the same, the flux has changed. Using this kind of reasoning, astronomers had a straightforward expectation for 3I Atlas. Over the month, from May to June, as it moved one astronomical unit closer, they predicted that its flux, its apparent brightness, should increase by a factor of about 1.5. A gentle brightening, consistent with a simple change in distance. But when they pulled the actual numbers from the test data, the story was different. The flux did not just creep up by 1.5 times. It rose by about a factor of 5. That is a much larger jump, a sign that something about the object itself was changing, not just its distance from the Sunday. In other words, 3I Atlas was not merely being lit more strongly. It was reflecting much more light than before, as though it had grown a larger, brighter surface for the sunlight to bounce off. This is one of the key clues that 3I Atlas is not a bare rock, not a simple asteroid, but a comet. As it warmed, material from beneath its outer layers began to escape, forming a coma of gas and dust around the solid nucleus. That cloud of tiny particles greatly increases the area that can scatter sunlight toward our telescopes. The sudden rise in flux is like a whisper from the object. I am changing. I am waking up under the sun's touch. So from this unexpected brightening, we learned that 3I Atlas is an active body, shedding material as it approached and passed perihelion. That alone would be interesting. But the light it reflects carries more information than just how much. Hidden in its details is another property, one that turns out to be even stranger: the polarization of that light. Polarization can be a tricky idea, so it helps to keep the explanation soft and simple. Light is a wave, and like any wave, it has a direction in which it wiggles. When sunlight hits a cloud of dust and gas and scatters, the directions of those wiggles can become organized in particular ways. By measuring how the light's polarization changes after bouncing off an object, astronomers can learn something about the size, shape, and texture of the particles doing the reflecting. For our purposes, we can think of two simple cases. If light from the sun hits the dust around 3I Atlas, and then scatters mostly off to the side, at right angles to its original path, we call the resulting polarization positive. The light has turned a corner, so to speak. If, instead, the light tends to bounce more directly back toward the source or along nearly the same line, we call that negative polarization. In that case, the scattered light is more aligned with its original travel direction. Most objects in space, including many comets and even other interstellar visitors, show mostly positive polarization under the conditions we can observe. 2I Borisov, that earlier interstellar comet, fit this familiar pattern. Its scattered light carried a positive polarization signature that matched other dusty bodies. 3I Atlas does not. Its light shows negative polarization, and not just a little bit. Among all of the objects ever measured in this way, 3I Atlas appears to have the most extreme negative polarization yet seen. For a quiet, icy traveler from the thick disk of our galaxy, that is very weird indeed. One way to think about that strange, negative light is as a quiet reminder. Not every star system in the galaxy plays by the same rules we are used to. What feels normal in the neighborhood of our sun might be rare or even impossible somewhere else. And what counts as ordinary around another star can look deeply odd to us. 3I Atlas carries those differences on its surface and in its cloud of dust, a small messenger of the idea that normal is always local. The odd polarization is only one part of that message. Another surprise hides in the coma itself, in the simple fact that it was there so early in the journey. When we talk about the strange behavior of this object, we keep coming back to that window of time between May and June when Tess was watching. During those weeks, 3I Atlas was still far from the Sun, beyond the orbit of Jupiter. At that point, it was more than 5 astronomical units away, in a region where sunlight is weak and the cold has had ages to settle in. Out there, typical comets are still locked up tight. They are like sealed boxes of ice and dust, their surfaces too cold for much to escape. Under ordinary circumstances, we do not expect to see a bright coma forming at 5 astronomical units. For most comets that were born in our own solar system, the real activity, the visible waking up, does not begin until they are closer in, somewhere between 3 and 4 astronomical units from the Sunday. Before that, they tend to remain frozen and quiet, without much gas flowing away. The reason is simple and familiar. Comets here are usually made mostly of water ice. Water, even in a vacuum, needs a fair amount of energy to break its solid bonds and move into a gas state. It does not start to sublimate in earnest until the sun's heat reaches a certain strength. So in most cases, we have to wait until a comet has come significantly closer in before those icy grains start to let go and a big, bright coma forms. 3I Atlas did not follow that pattern. When astronomers pointed more powerful telescopes at it and studied the light in detail, they found that the gas in its coma was not dominated by water at all. Instead, the main ingredient was carbon dioxide gas. There was some water vapor present, but the balance was very different from what we usually see. The ratio of carbon dioxide to water was roughly 8:1. That is almost the inverse of the pattern that feels normal to us when we look at comets born near home. To get a feel for what that means, you can think about something more familiar: dry ice. If you have ever seen a stage filled with low, rolling fog for a performance, or a bowl at a party pouring thick white vapor over the sides, you have met frozen carbon dioxide. Dry ice has to be made and stored at extremely low temperatures. As soon as it is pulled out into warmer air, it does not simply sit there. It starts to sublimate immediately, turning straight from solid into gas, spilling out that signature cloud that hugs the surface and tumbles downwards. 3I Atlas was doing something like that, but in the vast stillness of space. Far past Jupiter's orbit, in a region where water ice would normally stay rigid and calm, the carbon dioxide in this interstellar comet was already responding to the sun's distant warmth. Carbon dioxide ice does not need as much heat as water to begin escaping from its solid state. Because so much of the ice in or near the surface of 3I Atlas appears to be rich in frozen carbon dioxide, the comet could start forming a coma much earlier in its approach than we are used to seeing. So, that is one part of the answer. Its coma appeared too early because its main ingredient was a kind of ice that wakes more easily under a faint touch of sunlight. But the story did not freeze in that shape. Astronomers kept watching as the comet drew closer, and later, as it swept past perihelion and began to move away again. Over time, the balance between carbon dioxide and water in the coma began to shift. By late September, 3I Atlas had moved inward, passing through the region of Mars's orbit at a distance a little greater than 1.5 astronomical units from the Sunday. That is a place where ordinary solar system comets are very much awake, and water ice is commonly sublimating from their surfaces. At that stage, this interstellar visitor started releasing water vapor in enormous amounts. Estimates suggested a flow rate, like a fire hose, running at full power, streaming continuously into space. For something so small, that is an astonishing amount of water to be shedding. In fact, it was more water than astronomers would expect even from a standard, homegrown comet at that distance from the Sunday. The appearance was sudden, too. We had not seen any object go from relatively modest water emission to such a strong outpouring so quickly. It was as though a hidden reservoir had opened without warning, changing the balance in the coma in a rush. The same pattern of too early, too much, and strangely arranged showed up again when astronomers looked more closely at the tiny bits of metal mixed into the coma. During observations made in the summer, they detected a subtle but clear sign of nickel in the surrounding cloud of gas and dust. At the same time, they found no trace of iron. On its own, nickel is not especially rare in space, and neither is iron. Both are forged deep inside the hearts of massive, dying stars. When such a star reaches the end of its life, its core can no longer support the weight of all that matter. It collapses, and then, often, it explodes as a supernova, flinging its inner contents out into the surrounding galaxy. The nickel and iron, along with other heavy elements, become part of the raw material from which new stars and planets are made. Over cosmic time, this cycle repeats again and again, enriching the galaxy with metals. Because they are born together in the same furnace and travel out into space side by side, nickel and iron tend to show up together in the places where matter clumps again. Planets, moons, asteroids, and comets usually contain both, in proportions that are not wildly unbalanced. When scientists look at the composition of these bodies, they often find that where there is nickel, there is also iron. The two are old companions. So, seeing a modest amount of nickel in the coma of 3I Atlas, but no iron at all, raises a gentle, persistent question. Where did the iron go? What process could have taken matter that started out mixed and separated it so that, at least in the material being released at that moment, nickel was present and iron was not? It is like sifting flour and finding only one kind of grain in a mixture where you expected two. There is another layer of strangeness here. It is not just the imbalance between nickel and iron that stands out. It is the fact that any metal at all was showing up in the coma at that time and place. When those observations were made, 3I Atlas was still out beyond the orbit of Mars, moving through the region we call the asteroid belt. That part of the solar system is cold, with sunlight diluted over a wide area. Sublimation, the process of solids turning directly into gas, is driven by heat. It is easy to understand how carbon dioxide ice might start to sublimate there, because carbon dioxide responds to relatively gentle warmth, but metals like nickel normally require much higher temperatures to vaporize. The presence of nickel in the coma implies that something more complex is happening. One idea is that the carbon dioxide, as it bursts out of the ice in great quantities, acts like a powerful stream of invisible wind. As it escapes from cracks and pores in the comet's surface, it could carry along small atoms or clusters of nickel, lifting them up into the coma, even though the temperature would not be enough to make the metal itself truly evaporate on its own. In that picture, the nickel is being dragged, not cooked. Even that, though, does not fully explain the missing iron. If both metals began in the same mixture, why would the escaping gas carry one so much more readily than the other? Does it mean that the outer layers of 3I Atlas have been chemically sorted in some way we do not yet understand, with nickel more exposed and iron more deeply buried? Or does it point to differences in how the metals are bound up in minerals within the comet? For now, those questions remain open. The data simply tell us that at that point in the journey, we saw nickel and did not see iron. And that is not what we are used to. The pattern with metals ended up echoing the pattern with water. Just as the water vapor seemed to arrive late and in a sudden rush, iron also appeared in the coma only after some time had passed. By late September, as 3I Atlas moved closer in and the sun's influence grew stronger, astronomers began to detect iron lines in the light from the coma for the first time. Shortly thereafter, the balance between nickel and iron shifted towards something more familiar. The ratio of the two metals in the released material settled into a combination that looked much more like what we see in other comets and planetary bodies. In other words, as 3I Atlas plunged through the sun's warmth and then continued on its outward path, some of its stranger signatures began to soften. The carbon dioxide-heavy coma gave way to one rich in water vapor. The lonely nickel in the gas cloud was joined by iron, and the two metals returned to their usual partnership. In some respects, this interstellar visitor began to behave more and more like the comets that call our own solar system home. Yet the way it reached that normal behavior was anything but ordinary. It formed a bright coma at a distance, where most comets are still sleeping. It flashed carbon dioxide early and water late. It released nickel without iron in a region where metals should have been hard to liberate at all. 3I Atlas seems to move through stages of familiarity and strangeness, reminding us again and again that it was shaped under conditions different from the ones that shaped our local icy wanderers, and that it is taking its own, very unusual path toward looking, at a glance, like one of them. When you picture a comet, you might think first of its tail, that soft streak of light trailing behind as it moves through the dark. 3I Atlas has a tail as well, but even here it could not resist doing things a little differently. One more quiet oddity showed up in the way its tail first appeared and where it chose to point. Under normal circumstances, a comet's tail is shaped by the solar wind. The sun is constantly sending out a stream of particles and radiation that flows outward in every direction. When that invisible wind reaches the gas and dust in a comet's coma, it pushes on the lightest material and sweeps it away from the sunday. Because of that, we expect a comet's tail to point roughly opposite the sun, as if the star were blowing on it and stretching it out behind. With 3I Atlas, the first hint of a tail did not obey that simple picture. When observers began to notice structure in the coma back in the summer, they saw a feature pointing toward the sun instead of away. It looked as though the object had grown a small, sun-facing tail. For people who have spent their lives thinking of tails as things driven back by solar wind, that is enough to make you stop and look again. The likely explanation loops back to the early behavior we already noticed. Because 3I Atlas began to sublimate so far from the sun, its coma appeared at a distance, where the solar wind is still relatively gentle. There was gas and dust being released, but the push from the sun's outflow was not yet strong enough to immediately sweep that material away into a long, graceful tail. Instead, more of the cloud simply piled up on the warm side, the side facing the sun, where the ice was being heated most. The result, at first, was a kind of lopsided halo, thicker on the sunlit face. Only later, as the comet moved closer in and the solar wind grew stronger, did that cloud begin to be sculpted into the more familiar shape, material flowing away from the sun, drawn out into a proper tail. By September, 3I Atlas had developed a short, fan-shaped tail pointing in the expected direction, away from the star. In that respect, it started to behave like a more typical comet, even if the path it took to arrive there was unusual. It is worth remembering that the pictures we carry in our mind of comets, with long, dramatic streaks stretching halfway across the sky, come from a few especially striking examples. Not every comet grows a giant banner of light. The length and brightness of a tail depend on what the comet is made of, how active it is, and how close it comes to the sunday. Some wear only a modest veil. Others briefly unfurl something much grander. One of the most famous examples is Hale-Bopp, a comet observed in 1997. Its tail was enormous, a sweeping, luminous trail that could be seen from the Earth with the naked eye, even in places that were not perfectly dark. Part of the reason for that spectacular display was its distance. When Hale-Bopp was at its most dramatic, it was passing about 0.9 astronomical units from the Sun, roughly half an astronomical unit closer than 3I Atlas will ever come. Bathed in stronger light and feeling a more intense solar wind, it released more material and had that material pushed into a longer, brighter tail. 3I Atlas will never quite put on that kind of show for us, at least not from where we stand. Its path keeps it a little farther out, its activity different in timing and composition. Even so, there was a moment when we had a uniquely close vantage point, not from Earth, but from another world entirely. On October 3rd, this interstellar traveler passed within about 0.19 astronomical units of Mars. That was the closest it would come to any planet in the solar system, a brief, near encounter with the red world. For those of us who like to imagine the sky from other surfaces, this was a gift. Mars is not just an abstract point in space anymore. We have machines there, cameras sitting on its soil and circling above it. That meant we had a chance to see 3I Atlas not from home, but from a distant, rust-colored neighbor. One of those cameras belongs to the Perseverance rover, sitting on the surface of Mars, rolling slowly across its ancient rocks. Engineers pointed its instruments toward the region of sky where 3I Atlas would be, and let the rover look up. The image that came back is not the kind of crisp celestial portrait you might imagine. Perseverance's cameras were designed mainly to study the ground, nearby rocks, and the thin Martian atmosphere, not faint comets far away. To pull any sign of the object out of that darkness, the rover's camera had to take long exposures, keeping its electronic eye open for about 30 seconds at a time, letting as much light accumulate as possible. Even then, a single frame did not show much. Astronomers stacked several of those 30-second images on top of one another, combining them to enhance the faint signal. In the finished result, 3I Atlas appears not as a sharp dot, but as a small streak, a thin line drawn by its own motion during the long, layered glances. Another view came from higher up, from the ExoMars orbiter operated by the European Space Agency. Floating above Mars, this probe has a clearer view of space than any ground-based rover. Its instruments captured an image where 3I Atlas stands out a bit more cleanly against the background, a brighter point wrapped in a subtle glow. Even there, though, the object is still far away. The resolution is not high enough to cleanly separate the solid nucleus from the surrounding coma. We can see that something is there. We can tell it is active, but the fine details remain out of reach. To truly resolve the nucleus, to distinguish the core from its cloud with sharp clarity, we would need the power of a more specialized eye, like the high-resolution camera on NASA's Mars Reconnaissance Orbiter. That spacecraft carries one of the most capable telescopes in the Martian system, a lens that has given us detailed images of dune ripples and rover tracks on the surface below. In principle, it could also turn outward for a moment and try to catch a better look at 3I Atlas. As of now, though, no such close-up image has been shared, if it was taken at all. Sometimes, even when we know exactly what we would like to do with our instruments, real-world complications slow the work. Spacecraft have schedules and priorities. Teams on the ground have to divide their attention between many tasks, and occasionally some observations simply have to wait. For the moment, we make do with the streak from Perseverance and the distant glow from ExoMars, and we hold a small space in our curiosity for what a sharper view might someday reveal. In a way, that waiting fits the larger rhythm of our relationship with 3I Atlas. For now, the sun itself is still serving as a curtain. As the comet finishes its sweep through the inner solar system and moves onto its outbound leg, our line of sight from Earth passes dangerously close to the sun's brilliant face. The same glare that lights and reshapes the comet also hides it from our telescopes. We will not be able to study it comfortably from here again until early December, when the angle between the comet, the sun, and our world has shifted enough to bring it out of the worst of the brightness. By that time, 3I Atlas will have already passed its closest distance to the sun and will be steadily heading away from the inner planets. Around December 19th, it will come as close to Earth as it ever will on this visit, at a distance of about 1 astronomical unit or so. Even then, it will not sweep dramatically past our skies. It will remain a faint, specialized target for those with the equipment and patience to seek it. But from that vantage point, with the sun no longer directly in the way, we will be able to measure how much it has changed during its time in the spotlight. After that, the visitor will keep walking outward, leaving us behind. There is, however, one more close brush ahead. One more moment when another world will find itself nearby. On March 16th, 2026, 3I Atlas is expected to pass within about 0.36 astronomical units of Jupiter. That will be its last significant planetary encounter on this passage through our system, a near miss with the giant that dominates the outer regions. We do not have as many eyes around Jupiter as we do around Mars, but we do have one important witness, the Juno spacecraft. For years now, Juno has been looping around the gas giant, diving in close to study its storms, its magnetic field, and its deep, swirling interior. If its instruments and mission plan permit, it may be able to turn outward briefly and capture an image or some data from 3I Atlas as the comet passes through that neighborhood. By then, the object will be cooling again, moving away from the sun into colder, thinner light. Its activity will likely be reduced, the coma may shrink, the tail may grow fainter and shorter. But the surface will not be the same as it was before perihelion. The sun's heat, the outgassing of carbon dioxide and water, the release of dust and metals, all of that will have reshaped its outer layers in ways both visible and hidden. To compare measurements from before and after this close encounter with our star is to read, in a very small way, The story of how a brush with a new environment can alter a body that has spent billions of years in deep, quiet cold. That, in the end, may be one of the most interesting lessons that 3I Atlas offers. When we first realized it was an interstellar object, it was tempting to imagine that all of its peculiar traits must be fingerprints from its birthplace in the thick disk, its strange polarization, its early carbon dioxide coma, its odd nickel without iron signature. Certainly, some of those characteristics do reflect the conditions under which it formed and the materials it carries from long ago. But as we watch it change its coma, composition shifting, its metal ratios evolving, its tail appearing first in one direction and then another, it becomes easier to imagine a different possibility as well. Perhaps some of its weirdness is not ancient at all. Perhaps it has accumulated layers of strangeness along the way, like a traveler's coat that picks up stains and patches from every town it passes through. Dust from one encounter, radiation damage from another, a crust reworked by countless small bursts of sublimation near different stars. Right now, we can only guess at how much of what we see belongs to its original story and how much was written later, in quieter, scattered chapters across the galaxy. Each new observation adds a line or two to that book and erases some earlier assumptions. As 3I Atlas slips away, back toward the long between places from which it came, it leaves us with both more understanding and more open questions. There is a certain comfort in that too, knowing that even as this small wanderer fades from our view, the space it opened in our curiosity will linger, ready for the next brief visitor from the dark between the stars.